Hello everyone, thank you so much for watching my MASC oral presentation. As you can see, the title is An Investigation into Fundamental Frequency of Intact and Defective 3D Printed PLA Beams. During this research, we'll be explaining about test table setup, designing and manufacturing samples for both experimental vibration-based and tensile testing. In addition, results from tensile test and procedure were taken for running experimental modal test and result will be presented. Applicability of ANSYS modal test will be discussed and the steps were taken for running simulation modal test will be presented. Next, I'll be speaking about defect analysis. Crack was type of defect which was studied in this research. And at last, we'll have graphs, tables representing the effect of crack size and location on fundamental frequency of 3D printed PLA beam specimens. Few points in literature survey. ASTM D638-14 presents standards for tensile testing used to investigate Young's modulus of plastic materials. According to this standard, tensile testing is carried out for 3D printed PLA coupons because they behave in a similar way to plastic materials. Amongst different filaments which are used in 3D printing, such as polyether ether keten or PEK and acrylonitrile butadiene styrene or ABS, PLA or polylactic acid was chosen as the main feedstock for 3D printing specimens. PLA was found nearer to the market in compared to other types and also is a biodegradable thermoplastic material. In addition, the application of impulse excitation technique or IET as a type of non-destructive testing in material characterization and defect identification was surveyed in a number of literatures. Research significance and objectives. One of the main aims of the present study is to investigate the applicability of IET to evaluate material properties or elastic moduli of 3D printed PLA samples. The same method would be used to investigate the effect of imperfections on dynamic response of 3D printed PLA components. By comparing the Young's moduli which were obtained through conventional tensile testing to ones from inverse identification technique, applicability of suggested methodology will be validated. Also, by defining PLA as orthotropic material in ANSYS database, the fundamental frequency of 3D printed beam samples will be compared to those from experimental vibration-based tests. Using the same methodology and by employing IET, flexural strength of intentionally cracked beam samples will be studied in different crack size and location. Using the simulation ANSYS-based modal tests on 81 intentional embedded crack beam samples in wider range of locations and sizes, a crack depth and size versus fundamental frequency database will be presented. "15 tensile coupons, 5 for each build orientation, were manufactured according to ASTM standards. Also, same 3D printer and PLA spool was used to manufacture beam samples for experimental vibration-based test. 9 3D printed beam samples, 3 for each build direction, were manufactured. Samples manufactured in ZXY build orientation were 30 mm shorter in length. It was because that the 3D printer was restricted to manufacture samples with 250 mm in height. One might ask that, why you did not 3D print all the samples with the same shorter height? And I would reply, we faced this issue once we had manufactured samples in XYZ and ZXY, and then we realized we cannot manufacture ZXY beam samples with the same height. And this did not have any effect on analysis based on non-dimensional frequency equation. And as shown in the table below, The manufacturing parameters for both tensile testing and experimental vibration-based test samples are presented. And in this slide, we'll have the 3D printer, which was used to manufacture both tensile coupons and beams for vibration tests. The table below shows the mean values of elastic moduli for each build orientation. These results from tensile testings were considered as reference, and they were used to define orthotropic PLA in ANSYS database. The elastic moduli, which will be obtained through inverse identification method, will be compared with the results are shown in the table below. Experimental vibration-based tests. Bench power unit is responsible to provide 24-volt DC for laser interface, and laser interface transmits electricity to both amplifier and laser displacement sensors. Piezoelectric hammer also receives and transmits electricity and data using amplifier. All the information and data are transmitted to a PC using Ethernet connection from amplifier. The schematic view of the interconnected modular instruments are exhibited in the photo on the left. The photo on the right shows the displacement sensor lasers, which are vertically set up on a beam sample which is C-clamped in front of them. The distance between sample and lasers is 50 mm at the laser's focal point. Also, lasers are capturing displacement on the center line of the samples in order to capture pure flexural bending vibration. Time domain displacement spectrum in free vibration test is shown in the first photo. This spectrum of information is converted to fast Fourier transform or FFT graphs using Catman AP software. The maximum point in this graph represents the fundamental or first modal frequency of each sample. In each test, same maximum magnitude from each laser was obtained. One of the main aims of this study was to obtain Young's modulus of beam samples using experimental vibration-based tests. And using non-dimensional frequency equation, which is presented in this slide, the fundamental frequency, which were obtained through experimental modal test, can be calculated. It's noteworthy to mention that precise dimension measurement plays an important role in accuracy of the methodology. And finally, the table on the right shows the elastic moduli for all 9 beam samples in experimental modal tests. To the table, a close agreement is found between results achieved from traditional tensile testing and inverse identification technique, with maximum discrepancy of around 5%. Compared with traditional tensile testing, the application of IET can lead to a faster, easier, and more cost-efficient option for identification of material properties. The application of non-destructive testing in pulse excitation technique makes it possible to perform multiple experiments on the same sample. The elastic modulus obtained through IET overestimate those obtained through tensile testing, whereas for 2 other build direction, elastic moduli underestimate those from tensile testing. Further examination of data from the table reveals that the elastic moduli decreases from XYZ to XZY and from XZY to ZXY. The differences in directional elastic moduli can be associated with the build direction. Making analogy with fiber composite material in both XYZ and XZY build orientation, the fibers are along the axial force direction. As for ZXY, the extrudates are perpendicular to loading axis, and the main force holding the layers together is rather the adhesivity between layers, weaker than the extrudates. To simulate free vibration tests, ANSYS R2 and R3 academic version software was used. PLA as an orthotropic material was defined in ANSYS using values were obtained through tensile testing. In modeling beam samples, revised dimensions based on real sample measurements were used according to following steps. First, beam samples were manufactured using initial CAD modeling. After measuring width and thickness using vernier caliper, revised dimensions were used in CAD modeling in simulation model tests. Because mesh design is an important feature in simulation, the mesh type and size were studied in this research. Tetrahedral, hexahedral, polyhedral, and pyramid are four major types of 3D elements commonly used to discretize domain in FEM simulations. However, using ANSYS Academic, my access was limited to only tetrahedron and hexahedral elements. Convergence results for sample 11XYZ for both element types are shown in the figure on the left. As can be seen, 1.5 mm and 1.7 mm element size yield the same frequencies. The convergence has already been achieved. Number of hexahedron elements when compared to tetrahedron is found to be almost 3 times larger when the same and smallest element size used. This difference in number of elements was the only factor that convinced me to select hexahedron as the main mesh element type, because difference between the frequency results obtained from hexahedron and tetrahedron elements is negligible. The image on the right shows the difference between hexahedron and tetrahedron mesh type when applied to the beam sample. The table below represents the fundamental frequencies were obtained through both simulation ANSYS FEM-based and experimental vibration-based tests. In general, the average variances was found to be between 0.41% and 2.1%. The overall average variance was found to be very small, less than 1%. Finally, the highest percentage difference of 7.9% was associated with ZXY build direction, which in this case could again be attributed to inaccuracy in dimension measurement on uneven 3D printed samples surfaces. The original intended goal of this chapter was to propose a vibration-based structural health monitoring by combining the experimental and numerical modal analysis and inverse identification technique applied to intact and defective 3D printed PLA specimens. The main idea was to exploit laser-based vibration-based defect identification of existing cracks within the structure by comparing the natural frequency for intact and defective beams. The focus has been placed on single and multiple through thickness crack identification in 3D printed PLA beams. The goal was to devise a scheme to identify the number, size, and location of intentionally embedded cracks through the change in system's natural frequency. In this part of the study, an Anycubic Mega S 3D printer operated with Cura 4.4 software was employed to manufacture crack-embedded PLA beam samples. In addition, due to lack of access to PLA feedstocks originally used in the previous part of this research, the PLA from different producer was used. The same manufacturing process, design parameters, and dimensions as those used for intact 3D printed PLA test specimens were used to produce the defective samples. However, to avoid over-extrusion and a staircase look, I had to reduce the printing speed slightly, like less than 5%. Based on trial and error, it was found that minimum width of 1 mm should be designed in crack CAD modeling to achieve fully disjointed cracks within a 3D printed specimens, and the size of final printed crack width was found to be an average 0.7 mm. As shown in the images below, 2 sets of defective test specimens were manufactured, as well as 2 intact samples. Group A comprised of 5 specimens with a single mid-span crack of various depths, 120 mm from both ends, and Group B comprised of 5 specimens with double equidistant cracks. As can be seen from the tabulated and graphed data, the general trend shows that as the crack size of the crack increases, the fundamental frequency decreases. In addition, a doubly cracked specimen exhibits a lower frequency when compared to a singly cracked one with a similar defect size. However, some discrepancies can also be observed, which could be attributed to small changes and variation in dimensions of printed specimens measured and included in the FEM models. In comparison with the previous study, the recent results showed higher differences. This could be attributed to the fact that the recent study was done based on a specimen printed on much less expensive machine. In order to further investigate the problem in hand and to overcome shortcomings associated with limited number of test results, a large set of 81 defective models were generated and analyzed in ANSYS. The FEM-based modal analysis was then performed on defective samples with single crack of various depths and locations from fixed end. Crack was defined in 9 locations, spaced at every 24 mm from clamping zone with 9 different depths ranging from 2 to 18 mm. As can be observed from the graph data, the largest decrease in system's natural frequency is observed for the largest crack located at the closest proximity of the fixed end. The 2D plot and histogram associated with frequency versus crack depth are presented in figures below. For ease of comparison, 2D plot and histogram associated with frequency versus crack locations are shown too. Finally, using fourth-order polynomial regression equations applied on frequency data in 2D plot representing frequency versus crack depth, the following expressions for frequency as a function of crack depth at different crack locations are derived and presented in this table. And conclusions. In the second chapter, for XYZ build direction, the elastic modulus obtained through IET was found to overestimate the value obtained through tensile testing by 5%. For XZY and ZXY build directions, elastic moduli underestimate those from tensile testing by 2.2% and 4.1% respectively. The source of discrepancies should be further investigated. By comparing fundamental flexural frequencies obtained through both ANSYS FEM-based simulations and experimental IET, the average variances are found to be between 0.41% for XYZ and 2.1% for XZY build directions. The overall average variance is found to be very small, like less than 1%. Using experimental and FEM analysis, the effects of through thickness cracks on the vibration response of defective PLA beam, the general trend showed that as the size of the crack increases, the fundamental frequency decreases. In addition, a doubly cracked specimen exhibited lower frequency when compared to a singly cracked one with a similar defect size. According to results from ANSYS FEM tests and the 3D surface plots and graphs, we can conclude that if two of these parameters, such as frequency, crack depth, and crack locations are known, the third one can be extracted from the graphs. In the case where only one of the three parameters is known, then a family of solutions corresponding to the known one can be then extracted. Furthermore, using polynomial regression equations applied on frequency data, the expressions for frequency as a function of crack depth at different crack locations are derived. And at last, it is worth noting that due to some limitations caused by COVID-19 pandemic and closure of the university campus, the candidate was only able to conduct limited number of experimental free vibration tests on deliberately cracked samples. And finally, for the future work, I would recommend increasing the number of dimension measurement points used for modeling specimens from 5 to 10 in order to increase accuracy of the measurements. Further investigation into the source of discrepancies, such as over and underestimation in elastic moduli for both IET and tensile testing. Employing AI in crack detection using more extensive database similar to those obtained and presented in 3D surface results, for example, considering 2 and multiple cracks. And at last, as suggested by Bornemann and Hashemi in 2018, including frequencies of higher modes in the defect identification process could help to recognize larger number of cracks. Therefore, as a next step, including effects of second modal frequencies in the process is recommended. And in the end, thank you so much for your attention.